Hello everyone, welcome to the Hi-Fi School. In this video we are going to look at chapter 5, Data Handling of 8th class CBSE Mathematics. The first section is 5.1, Looking for Information. So where are we going to look for the information? We are going to look for the information in a given data. Now what is data? Data is raw information available in numeric form, text form, or in visual form such as photos or videos. So as we discussed, data can be numeric, data can be in the text form, data can be in audio form, data can be in video form, data can be in images form. All these different forms there can be representation of information, or there can be data. In this chapter we are going to focus on data available in numeric form. Okay, numeric form. So what is numeric form? 1, 2, 3, 4, 3.4, 5.6 in this form, in the form of numerals, in the form of numbers. As we know that we look for information in the given data. What we look for? We look for information in the given data. Now it's easier to look for information in given data when data is represented graphically. Okay, for example, let's say we are having 2, 3, 54, 93, 20, 13, and then we are having some information like 6, 8, 9, 6, 10, 11, 15, 29, 30, 86, and so on and so forth. And we are having some more information available here. It's all random information what we have here, numerically represented. Okay, for example, we are having 19, 20, 86, 84, 89, 38, 54, 60. For example, these all are some measurement of three different things. For example, these are measurements of different fruits, okay, in millimeters, length of different fruits in millimeters. Okay, and now we want to find out like what is the probably this color, yellow color is for mango, and we want to find out like what is the maximum length of mango we have. To draw such information from this kind of data which is only given in the number, right, it's difficult. But if we graphically represent this data, we categorize and then we graphically represent this data using pictograph or a bar graph or a double bar graph, it's gonna be easier to look for information in that data. Okay, so for example, we convert this into a bar graph and say that this is mango, pomegranate in red color, pomegranate, and then probably we are having this green color kiwi. Okay, and length of all these fruits. So we find out pomegranate height something like this, and then kiwi height something like this. I mean randomly. Okay, so mango ideally should be higher than kiwi, but this is how we have categorized in a bar graph. We represented this maximum height of these three fruits. Okay, now it will be easier. Now we can quickly say that which fruit is having the maximum height. We can quickly say that kiwi is having maximum height. Okay, which fruit is having minimum height out of the three categories available. We can quickly say okay, pomegranate is having minimum height. Okay, so it would be easier if we graphically represent data. What I mean to say is, instead of all these numbers written, like these are all probably 20-30 numbers here, but if it becomes 1000, 2000, 10,000 numbers, it would be difficult to make sense of that data. It will be difficult to look for information in that data if the data is just given as numbers. Okay, so this is why we represent the data graphically so that it's easier to look for information in that data. So first graphical representation we are going to see here is pictograph. Okay, as the name suggests, this graph is having picture in it. We are representing something using picture. Okay, for example, let's see that we are having orange. Okay, so let's say that this one orange represent 1000 oranges. Okay, so basically when we are having these two oranges, then that means we are having 2000 oranges. Okay, and let's say like I'm having an orange farm, and in year 2019 I had 10,000 oranges came out of that farm. Okay, and in year 2020 it was not a good season, so I had only 6,000 oranges came out of that farm. Okay, again in year 2021 there was a very good crop and I got 15,000 oranges from the same farm. Okay, so like this we are having and we want to represent this information using this information currently available in all in number form, and we want to represent that as a pictograph. Okay, so then we will represent this as a pictograph. 2019, 2020, 2021. Okay, and then we will say that in 2019 we are having 10,000, so we'll make this 10. 9, 10. Okay, now in the year 2020 we had 6, so we'll make them 6. Something like this. Okay, and in the year 2021 we are having 15,000, so we'll make 15 such oranges. Okay, and for example one orange is 1,000 oranges. So for example let's say that we are having a number in year 2022, we are having number of oranges as 5,500 oranges. Okay, very bad crop, and now we want to represent it 22. So 5,000 means 1, 2, 3, 4, 5, and we are having 500. Not so we cannot make sixth, we have to make half of it. Okay, like this. Okay, so these are 5,000 and half of 1,000 is 500. So total 5,000 plus 500 is 5,500. So this is how we represent given data in a pictograph. So in some questions we can be given this information that this shape of an orange represent 1,000 oranges and this pictograph, and we can be asked like for some information, look for information in this pictograph. What information? Like in year 2020 how many oranges came out of the farm, how many oranges were grown in the farm. So then based on this information we will count in this pictograph 1, 2, 3, 4, 5, 6 and 6 such shapes, and one shape is actually for 1,000 oranges, 6 into 1,000, 6,000 oranges came out of that farm. This is how we will draw information from this pictograph. Now let us look at what is bar graph. Okay, bar graph essentially is about when we are having categories, then in different categories we represent data. For example, in this data we are having what categories do we have? These numbers we have, but for what these numbers are? These numbers are yield of orange in a given farm in 2019, 2020, 2021. So these are categorized year wise categories. Okay, so 2019 there is a category, 2020 there is a category, 2021 category, 2022 category like this. So these are categories. So when we divide data into categories, so we can use bar graph when we are having categories and its corresponding number. Okay, so it can be any category. Production of car in year 2019, these many thousand cars were produced, Toyota cars were produced, for example. Any kind of category and its corresponding number. Height of 8th class, maximum height of 8th class student, like, or number of students in class 8th, some number of students in class 9th, some number. So here the category is 8th, 9th, or say for 10th. These classes are the categories here, and the corresponding number of students are here. So numbers categorized. Okay, so we represent such categorized numbers using a bar graph. So 2019, so for example we are having something like this here. Each slot represents some 1000. So this is 1000, this is 2000, this is 3000, this is 4000, this is 5000, this is 6000, this is 7000, 8000, 9000, 10,000, 11,000, 12,000, something like this. Okay, and now we are having this for 2019, we are having 10,000. So let's say 7, 8, 9, 10,000 is coming here. Okay, 11k is coming here, 12k is coming here. So 10,000. So first one, this bar. Okay, as the name suggests, this is a bar graph. So we have drawn a bar. Okay, this is a bar. Okay, this bar we have drawn. It's kind of a rectangle. Okay, rectangle of a height 10k. Okay, for 2019 category. 2020 category, it should be 6,000. 6 is here. Okay, let's take a different color. Okay, let's take a different color, green color, and then this is 6,000 here. So we'll make this category 2020 with a height, a rectangle of 6,000 height. Okay, on this scale, this is what number of oranges. Number of oranges. This is important to write this information, that what this axis, y-axis represents, and what this axis represents the year. Okay, and 2021 we are having 15,000 out of this chart, but still we will put something like this. Okay, and this will continue. Basically this will continue into till 15,000. Okay, in year 2022 we are having 5,500. So somewhere around here. Okay, this will come somewhere around here. Let's put it in the blue color, and then we'll make again a rectangle of height 5,500. So this is how we make a bar chart or bar graph. Now double bar graph. Okay, the bar graph was having information of for one set of data. Okay, so for one set of data, like for oranges. Okay, oranges in different years, yield of oranges in different years. So that was one set of data. Now double bar graph we can make graph when we are having two sets of data. For example, I am having two farms, one of orange and one of apples. Okay, so for example, in 2019 in my apple farm there were, let's say, 6,000 apples. Okay, 1, 2, and again one apple, one this shape represent 1,000 apples, and I had 6,000 apples came out from the farm in 2019. So there's 6,000 apples. Again, like let's say 7,000 apple came out in 2020. 1, 2, 3, 4, 5, 6, 7. Okay, in 2021 let's say only 3,000 apples came. Okay, in 2022 it was again very bad for the apple, and 4,000 apples came out of it. Okay, so now we are having for these yearly categories, 2019 yield of 2019 of oranges, yield of orange in 2020, yield of orange in 2021, yield of orange in 2022, also yield of apples in 2019, 2020, 21 and 22. So we are having two sets of data, one for apple and one for orange. To represent such a data graphically, we can use double bar graph. How can we do that? Let's do this. Okay, so the categories are going to remain same: 2019, 2020, 2021, 2022. But in each category, we are going to have data for oranges and apples. So oranges were, let's say, now again we are putting these points here. Okay, so these points here, this is essentially 1K, 2K, 3K means 3000, 4K means 4000, 5K means 5000, 6K, 7K, 8K, 9K, 10K, 11K, 12K, 13K, 14K, 15K, 16K. Okay, and 2019 we are having how many? 2019 we had 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, 2019 we have 9,000 or 10,000 perhaps, like we made it 10,000, so perhaps we had 10,000 oranges came out of the farm in 2019. So we'll put it like this: 10,000 oranges came in 2019. Here is 10. So we'll make a bar or a rectangle of the height 10,000 for the year 2019. In the same year we had 6,000 apples. Okay, so in the same year, side by side, we can put this is 6,000 here, we can put one more graph here, one more bar here. Okay, and so the like this, like we are making double bar. Okay, again similarly for 2020, how many oranges were here? 1, 2, 3, 4, 6,000 oranges came. Okay, so again put the yellow color here, 6,000 oranges came. 6,000, let's see, this is 6,000 oranges came, and only 3,000 apples came. Okay, so in yellow color, in red color, 3,000 apples came. Okay, so like this we are representing the data. In 2021 we are having whatever is the number. Okay, 2021 we had around 15,000, I think. So there's 15,000. So yellow, 15,000 oranges were here, something like this, and this rectangle of 15,000 height to represent 15,000 oranges yield in year 2021, and similarly 4,000 apples in the year 2021. So 4K is just here. Okay, so this is how we are representing two sets of data: oranges and apples, production or the yield of oranges and apples in different years starting 2019 ending with 2022. For given 4 years we are tracking yield of oranges and apples. So for this we are having two sets of data: apples data and oranges data for these 4 years. Okay, and both sets we are representing in one graph, and that graph is a double bar graph. Now in this section 5.2 we are going to discuss about organizing data. So what we have is raw data, for example, or disorganized data which is not organized. Such a data we are going to organize in a way with which we can see certain order in data, and organized data can help us better in terms of looking for the information in it. Let's say we are having a raw data of number of heartbeats per second in an exercise session. Okay, for example, let's see we are having 72 heartbeats per second, 82, 75, 72, 83, 90, 105, 110, 140, 139, 120, 125, 120, 90, 83, okay, 72, 145, so on and so forth. Now let's organize this data. Let's organize this number of heartbeats per second data, raw data we have. For example, we have measured these many number of times in an exercise session what is the current heart number of heartbeats per second, and now we are going to organize this data. Okay, in order to organize the data, we'll have to see how many times. For example, we'll take a note of the first heartbeats per second, which is 72, and we are going to look for it how many times it has come in the entire raw data collection. So 72 came once, 72 came twice, 72 came thrice, so 3 times it has come here. So this is what this mark, what we are marking it is a tally mark. Okay, we mark tally mark like this: 1 2 3 4 and 5, 1 2 3 4 and 5. For example, we need to write 6, then 1 2 3 4 5 and 6, like this. This is how we do tally marking. Okay, so that's what the tally marking is. And what is the frequency? Frequency is 3. Okay, 72 came thrice, so frequency of 72 is 3. Similarly, we are going to take a note of 82. How many times 82 has come? 82 came once, and that's it. 82 came only once. Now third one is 75. Let's see 75. How many times 75 has come? 75 came once. That's it. 75 also came only once. 83 came once, and then 83 came twice. So 83 came twice. Now 90 came once, and 90 came twice. 90 also came twice. And similarly 105 came once, and it did not come again. Okay, 110. So this is how I have written for all these heartbeats per second. I have written its tally, like 82 came once, 139 came once, 120 came twice, so 1 and 2, like this. Okay, so this is what the tally table is, and the frequency of 72 is 3, frequency of 82 is 1, frequency of 75 is 1, frequency of 83 is 1. So if I write it somewhere here, frequency, this is tally. Okay, if I write somewhere here the frequency, this is again tally. And if I write the frequency here, then I can write the frequency of here is 3. Okay, frequency of this one is 1. So this is like 1. Okay, tally 1 is a straight line. Okay, it's not like 1 is this one. So this is 2, this is 2, this is 1 again, this is 1 again. The frequency of this 140 is 1, frequency of 139 is 1, frequency of 120 is 2, frequency of 125 is 1, frequency of 145 is 1. So this is tally mark, and this is frequency. Okay, so that's how this is our frequency distribution table. This is when we write frequency corresponding to a data point, or this is the data point. 72 is out of this data, this 72 heartbeats per second. So how many times it has come? 3. So this is how we are writing, like which data has come how many times in the given data is the frequency of that data. 72 came thrice, so 72 frequency is 3. So it has come 3 times in this given set of raw data. So that's what the frequency distribution table is, how the frequency of a data is distributed, right? So like this has come 3 times, so 3, 82 has come 1 time, so frequency of 82 is 1, and like that. That's what is called a frequency distribution table. Now number 4, class interval. So class interval comes into picture when we classify this data, given data, into ranges, into classes. Okay, so how do we classify this data? Let's say we classify this data into classes such as data which is in between 70 and 80, data which is in between 80 and 90. Okay, data which is in between 90, 100, 100, 110, 110, 120, 120, 130, 130, 140, 140, 150. Now we see that this value is same as this value. Okay, the last value of this class is the first value of this class. So in case if there is a data, if there is a number 80, if there is a heartbeats per second in this given raw data is of 80, then whether it's going to come in this class or in this class. So I mean, we cannot put 80 in both the classes because this is 70 to 80. This can come here also. 80 can come here also. 80 can come here also. But we need to adopt a convention by which we will consider this value, this kind of value, 80 for example, which is there in both the classes. We will consider only in one class. So as a convention, probably we can consider this value 80 in this class, in the higher class. Okay, in the higher class. So which is the higher class? 70 to 80. This 80 value, this is the higher class for the value 80. So we will consider it here instead of here. Okay, wherever it is the lower limit, we will consider it. Okay, so now let's start putting these values. 70 to 80. What are the values between 70 to 80? So we know that these are the values in between 70 to 80. 1, 2. There are two values between 70 to 80. So we will put it as, let's put it in the form of frequency table. 1, 2, and not in the form of in the form of telemarking. 1, 2. Okay, and in the form of frequency, it is 2. Okay. Now 80 to 90. Now we know that 80 to 90. What are the values? This is 80 to 90, 82, 83. Okay, 90 we will not consider here. 90 we will consider in this one, in this class. Okay, so 80 to 90. So 80 to 90 also we are having two values. So in the telemarking we will put this two lines and frequency as 2. In 90 to 100, this 90 will consider in 90 to 100. Okay, so 90 to 100, there is only one value which is in between 90 to 100, which is 90. Okay, so we'll not put 90 here, we'll put 90 here in this one where there is a lower limit 90. Okay, so one value, frequency 1. 100 to 110, 110. Again 110 will not consider here, we'll consider here. Okay, so 105, yes, 105 is in between 100. Yes, so 1, 1. 110 will consider here. 1, there is only one value, so 110 will consider here. 1, 120, 130, 120 is here. Okay, so 120 we are not considered in this one, will not consider here, will consider here. So 120 here. Okay, 125 here. That's it. Okay, 130, 130, 140. So 140 will not consider, will consider in the next class, higher class. Okay, so will not consider it here in this one. So what is, yeah, 139 will consider. Okay, so 139 only one value, frequency 1. 140 will consider here 1. 140 to 150, 140 and 145, two values. So on the telemarking 1, 2 and the values are 2. Frequency is 2. Okay, so this is what our telemarking and frequency table is. Frequency is. Okay, and this is what classes are. 70 to 80 is one class, 80 to 90 is one class, 90 to 100 is one class. This is what the class is. Okay, and this class can have any width. In our case, the width of this class is 10. Okay, because this is 10 wide. 70 to 80 difference between lower and higher value. Okay, lower class limit, upper class limit. Lower class limit is 70, Upper class limit is 80 for this class, and the width or the size of the class is 10, because the difference between 80 and 70 is 10. For this class, lower class limit is 80, upper class limit is 90, and width remains the same, which is 10. Now here what we have is an organized data. Okay, we have the data, but it is an organized data. Okay, it is not raw data, it is already organized. Okay, we have organized this data of income of different workers. Okay, so many workers. Okay, so we have, what we have done is, and different workers earn different amount in a day. Okay, some workers earn, for example, 100 to 125 rupees, which is, very low, but let's say that it's a daily income, 100 to 125 rupees per day. Some workers earn this amount. Some workers earn 125 to, in between 125 to 150 rupees a day, and similarly 300 to 325 rupees a day. Some workers earn that amount. So what we have done, so the data, there are different classes, there are different income classes, per day income classes that we have organized our data in, and number of workers each of these classes have. So 100 and in between 100 and 100 to 125 rupees a day, we are having 45 workers. In between 125 to 150 rupees a day, we are having 25 workers. In between 150 to 175 rupees a day, we are having 55 workers, so on and so forth. So this is an organized data. Okay, now based on this organized data, we can answer questions, some questions. Okay, so for example, what is the size of the class interval? So we can see here, these are our classes. Okay, and size of the class is the difference between its upper limit and lower limit. So 125 minus 100 is 25. Okay, so this class size is repeated. Size of the class interval is repeated across that. It's uniform within the data. Okay, so difference between 150, upper limit here of this class interval, 150 and 125 is again 25. So size of the class interval is 25. Okay, what is the highest frequency? So now we can see this is the frequency. So frequency means number of workers belonging to a class. That's the frequency. These many workers come into that class. So that's the frequency of the worker. Okay, frequency of the workers belonging to that class. So what is the highest? We can immediately spot that 140 is the highest number in the frequency column. So what is the highest frequency? 140 belonging to this class, 200 to 225 rupees a day. Okay, daily income. Lowest frequency, we can quickly scan through and find out this 25 or this 20 is the lowest frequency. Okay, so 20 is the lowest frequency. So in between 300 to 325, the highest most class of the daily income, or highest most daily income group is having the least number of people, which is sort of expected. Okay, upper limit of the class, so lowest frequency where upper limit of the class 250 to 275. So 250 to 275, upper limit of this class is 275. Okay, because the lower limit of this class is 250, upper limit is 275. Okay, so 275 is the answer for this. Classes with the same frequency, we need to find out which are the classes having same frequency. Okay, so which number is repeating? This 55, this is also 55. So these classes, the 150, 175 class and 220, 225 and 250 class are having same frequency. So we can write it 150 to 175 in this class, and 225 to 250. These classes are having same frequency. Any other number which is having the same frequency available? 45 is not repeating, 25 is not repeating, 55 has repeated. We have already noted it with the frequency for these two classes are 55. Okay, 125 is not repeating, 140 is not repeating, 35 is not repeating, 50 is not repeating, 20 is not repeating. So there is only one frequency which is being repeated in the two classes. So we have written it as an answer here. So let us take now one example where we need to construct a frequency table. Okay, for the given data of weights of 20 students of a class. Okay, so these are the weights given for the 20 students of a class. These are all on kgs. Okay, and we need to classify the data into intervals like 30 to 35 kg, 35 kg to 40 kg, so on and so forth. Okay, so we'll have to count how many students are there in between 30 kg to 35 kg. So that's going to be frequency for this class. 35 kg to 45 kg, that's going to be frequency for this class, so on and so forth. So we'll first put a column name as weight classes, wherein we'll put 30 to 35 kg and 35 to 40 kg, 40 to 45 kg, 45 to 50 kg, 50 to 55 kg, 55 to 60 kg, 60 to 65 kg. That's it. And then we'll put the frequency here. Okay, so 30 to 35, let's find out. Now what is in between 30 kg to 35 kg? So 33 comes in between. Okay, 31 comes in between, 34 comes in between. Anything else? No. 36 is out of 35, so it does not come. Anything else? No. 38 and 39 are also, so there is nothing else. So how many students are there in the weight range of 30 kg to 35 kg? 3. Okay, now 35 to 40. 35 to 40. That 40 we will not consider here, because 40 we will consider in this higher class. Okay, as a convention. Okay, we will not consider it in both, we will consider it in only one, and that would be the higher class. Okay, where 40 is the lower limit. Understood? Okay, now 35 to 40. Okay, so 38 comes in between 35 to 40. Okay, what else comes? 35 to 40. Anything? This 36 comes 2. And anything else? This one, this one, this one. How many? 1, 2, 3, 4. So 35 to 40 we are having 4 students. Now 45 to 40, of course 40. We will start with this one. Okay, 40 to 45. Okay, no, this is more than 45. No, 40 to 45. This one is here, this one is here, this one is here, this one is here, this is not here. Okay, so 1, 2, 3, 4, 5. So frequency of this class 40 to 45 kg class is 5. Now I have filled in this thing for frequency for all the other classes. Okay, please note that this 55, what we have here, this 55 is got counted here instead of here. We did not count it in the lower class, we counted in the upper class. Similarly 60 was there. Okay, 60 was there, so 60 is this bordering value which comes into the both classes. In the lower class it comes at the as a higher limit, and in the higher class it comes as a lower limit. So we'll consider it here where it is a lower limit. We'll consider it in the higher class as a convention. Okay, so this is how we construct a frequency table. In the previous sections we have seen bar graphs. Okay, 2 types of bar graphs we have seen, bar graph and double bar graph. Okay, and that was to do with the categories. Now plotting the categories with its frequencies. For example, in 2019 category, yield of oranges in 2019 from a farm. Okay, yield of oranges in 2020 from a farm. Yield of oranges in 2021. Yield of oranges in 2022. So these are the categories. 2019 category yield, 2020 category yield, like this. and there would be certain numbers, like these many oranges came out of the farm in 2019, these many oranges came out in 2020, and so on and so forth. So we, for the different categories, we were plotting the numbers, yeah, whatever the number of oranges, like this. So for different categories we were plotting the data. So that was to do with the bar chart. In double bar chart, there were two categories, two sets of data we were comparing together, right? For example, oranges and apples. So we have seen that, like in 2019, what was the yield of oranges and apples? Oranges and apples, oranges and apples, like this. So two sets of data we were comparing together. Okay. So 2019, these many oranges were produced. For example, this is 2000, whatever, right? This is 1800 or something like this, right? On the scale, two sets of data are represented. So that was double bar chart or double bar graph. Okay. Single bar graph, which was having single bar. Bars are what? These are simply rectangles representing a data point, okay, on that particular category axis, and number belonging to that category, or the frequency belonging to that category, right? Now we are looking here in this subsection, we are looking at the bars with a difference. Okay, so what can be the difference? Like we can see that these are categories, they're different categories, right? And these are categories, and these are not joined together as such. Okay, these are all separate on the x-axis. Categories are separate on the x-axis. Okay, but there can be a continuous sort of class intervals, and for which we draw a bar graph with a difference, right? For example, here this is 0 to 10, 10 to 20, 20 to 30, 30 to 40, 40 to 45, when the data is of continuous nature, right? And when the class intervals are of continuous nature, right? So that's when the bar of the difference comes into the picture. Okay, so 45 to 50, 50 to 60. So this is our class interval. Okay, and this is our frequency axis. It can be anything. Okay, for example, these many marks and these many students. So from 0 to 10 marks have been received by 2 students. 10 marks to 20 marks in a maths paper, okay, were received by 10 students, so on and so forth. Okay, so this class can belong to marks of the students. Okay, and lower limit 0, higher limit 10, 2 students. Lower limit 10, higher limit 20, in between this 10 students, so on and so forth. Okay, so let's plot it. So we can put it like this: 10, 20, 30, 40, something like that, on an interval of 5, 5, 10, 15, 5, 10, 5, 10, 15, 20, 25. Okay, so that's the limit here. So let's now start plotting. 0 to 2, now we have 2 students here. Okay, 0 to 10, 2 students. 10 marks to 20 marks, we have 10 students. 10 to 20, 10 to 20, how many? 10. So this is gonna come here like this. Okay, 20 to 30, we are having 21 students, slightly more than 20. Let's do this like this. Okay, 30 to 40, 30 to 40, 19, slightly less than this one, 19. 50, yeah, 40 to 50, 7 students, slightly less than this one, 10. Okay, and 50 to 60, only 1 student. Okay, these many marks, very high marks, have been received by only 1 student. Okay, so 1 is 1, something like this. Now observe one thing in this. In the bar charts, regular bar charts or bar graphs, single bar or double bar graphs, we did not have these bars adjacent to each other. They were not joined. Okay, they were not sort of continuous in nature, right? So those they belong to different categories here. There were different categories here. It can be anything. These are the years category, for example. Okay, it can be anything. Okay, so number of mangoes, like number of mangoes, number of oranges, number of kiwis, like this. These are the categories like this. But here, and this kind of a chart, right, this scale is continuous, like you see, and this is why these bars have joined each other. They are adjacent to each other. So when a class intervals do not have any gap in between, these are continuous, they are adjacent to each other. They are not, these class intervals are not having any gap in between, they are continuous in nature, right? So this is why these bars are adjacent to each other. There is no gap in between these bars. So this is why these bars are with a difference, and since there is a difference, there is a different name as well. The name of this bar chart, this kind of bar chart with a difference, is histogram. Okay, histogram, mainly used for representing continuous data. Okay, now in this section 5.4 we will discuss circle graph or pie chart. As the name suggests, circle graph is having a shape of a circle. Okay, so circle graph looks like a circle, right? In any graph, as we know, we actually represent multiple values of a quantity, right? In any graph we represent multiple value of a quantity. For example, these are heights of a student in class 8th. Okay, student number 1 2 3 4 5 6. What is the quantity here? Height of the class, height of the students of class 8th. That's the quantity. And what are the multiple values here? Say 3 feet 5 inches, 4 feet 2 inches, 4 feet 3 inches, so on and so forth. Okay, so in any graph we represent multiple values of a quantity or multiple values of multiple quantities. That's what we graphically represent in a graph. Okay, so in this circle graph, in order to represent multiple values of a quantity, what we need to do, how can we represent multiple values of a quantity? We will represent it using different sizes of this pie. Okay, if the value of the quantity is high, then this pie size will be bigger. If the value of a quantity is small, then the pie size will be smaller, like this one, this green one. The pie is of a smaller size. Okay, like this red one is a bigger size. So if the value of a quantity is bigger, then this pie size is bigger. This is why this chart also known as pie chart. Now let us take an example for a quantity. Let's say the time is spent by a child during a day. Okay, so time is the quantity spent by a child. Time spent by a child, okay, in a day. So basically in a day, okay, so time is going to vary in a day. In a day is what? 24 hours. Let's say we are going to measure this time spent in hours, like we can measure in minutes and seconds also, but let's say for simplicity we are going to measure it in hours. Okay, within a day. So basically if we are going to represent this quantity in a circle graph or in pie chart, we'll have to draw a circle. Okay, so this circle basically is going to represent, this complete circle is going to represent how much? 24 hours. Okay, this complete circle is 24 hours. And within these 24 hours, in a day, right, in a day, so we are going to represent a day or 24 hours, like how many hours have been spent in something, sleeping, going to school, doing some homework, or doing some play. Okay, playing in a playground, something like this. So we are going to split these 24 hours spent by a child differently. For example, this 8 hours something, and then let's say another 10 hours something. Okay, and so how many 18 hours are already gone? So how many 8 more hours are left? Okay, so let's divide it into, let's say, 4 hours here and 4 hours here. It's looking bigger than 4 hours, but okay. Let's say 8 hours are for school, may include going to school, coming back from school, like this. 10 hours for sleep, an adequate time. Let's say 4 hours. 4 hours for play, playing in the park, playing in home, playing with neighbors, etc., etc. Okay, and for all other activities, this remaining 4 hours. Okay, for all other activities, remaining 4 hours. So 18 plus 8 is 24. Okay, so all 24 hours have been spent like this. So this is what a pie chart for time spent by a child in a day, quantity. Now different information we can deduce from this circle graph or pie chart. Like for example, school time is 8 hours. Okay, so total time is 24 hours. So 8 hours divided by 24 hours. That means this 8 hours is what? Is 1/3 of the total time. Is 1/3 of the total time in a day, right? So 1/3 of total time in a day. Let's say the total time in a day is 24 hours, which is 100% of the time. Then 1/3 of the total time is 33% or so. Okay, so 33% of a day a child spends in school according to this graph. Okay, so this way we can deduce different numbers out of the circle chart, circle graph, or a pie chart. In the next subsection 5.4.1, we will draw a pie chart for this table. So what is this table about? This table is about, there are 3 flavors, chocolate, vanilla, and other flavors. There are basically 3 categories of the flavor. And there is a quantity of percentage of the students preferring the flavors. Okay. So we are having, say, 100% of the students of a class, of a school, or whatever. Like let's say there are in a given set, all is out of all the students, out of 100% of the students, 50% students prefer chocolate flavor. And out of all the students means out of this circle, 50% is going to be represented by chocolate flavor, 25% is going to be represented by vanilla flavor. So let's say, how do we draw 50% of anything? We divide that anything into half. Okay, for example, 50% of this chocolate bar is half. Give me half of it. Give me 50% of it. So to represent this chocolate in this, the percentage of this chocolate in this pie chart is dividing this circle into 2 halves. Okay, once it is divided into 2 halves, okay, so how do we divide a circle into 2 halves? We'll have to find out a center. Okay, and then we can put a straight line here. Okay, from this center. Okay, so that this line should pass through center of the circle. Okay, that way we will divide this circle into 2 halves. Okay, if we cross the circle like this or like this, it is not going to divide it into halves. Okay, but I will cross this from the, if this line is going to cross from the center, this is going to divide into 2 equal halves. Okay, whether the line is, or you are going to draw the line like this, then this half and this half. Okay, this half and the other half, this half. Or if the line is crossing like this, which was drawn originally like this, then this is the first half, this is the second half. So either of the half we will put as 50%, and that belongs to chocolate. Let's put some chocolate like color. Not exactly, it's slightly gold, but let's say it's a chocolate color. Okay, and this is 50%. How much? 50%. And this is chocolate. Okay, now we are having 25% for vanilla. 25% is what? 25% is 1/4 of 100%. 25, 25 plus 25 plus 25 plus 25 is 100. So this 25 is 1/4 of 100. Okay, so what is 1/4 of a circle? This is 1/4 of a circle. This is, so if we put, this is 1/4 of a circle. Okay, that can be any side, but since this side is already covered by 50% chocolate, this remaining 25% we can put as for vanilla, whatever is the color of this vanilla. Okay, 25%, and the remaining 25% is all other flavors. Okay, other flavors. Okay, so this is how for this given table we have drawn a pie chart representing all the percentages of a quantity, this percentage of students preferring the flavors, and there are different values of this percentage of students. 50% prefer chocolate, 25% prefer vanilla, 25% prefer other flavors, and we have represented this quantity, multiple values of these quantity in this pie chart. Okay, so pie charts we will either have, for example, values mentioned in percentages or values mentioned in numbers. So when it is mentioned in percentages, then we know that the total circle is 100%, right? Total circle is 100%. One circle, 100%, right? And then division of these circles will be done based on the percentages of the values. Okay, so that is the kind of thing we will adopt, like we have done in this case. Like percentages were given, for circle is 100%, and this 100 we have divided according to the values given. But if the values are given, for example 8 hours, 2 hours, 3 hours, then we'll have to see like what are we dividing? Are we dividing a day? Are these values of something from a day, or from a, like, are these, if they are months, for example, they may be from a month. Then the total number of months in a year, for example, are 12. Then these values should add up to, different values given should add up to 12, something like this, right? Then only we can represent, for example, we are representing a quantity in a year, then and there are different months given, then we'll have to, these number of months should add up to 12. Okay, like 1 month we have spent studying chemistry, 1 month we have spent studying social science, 8 months we have spent in studying mathematics, and remaining 2 months we have spent studying physics, let's say that. Okay, so this is how this is also can be an example how do we divide numbers. So in case of putting these numbers into this pie chart, we should know like what are these numbers, if they are they months, are they hours, what are they, right? So this actually we estimated based on the simple facts that 50% is half of anything and 25% is quarter of anything, and so on and so forth. But we can, these percentage at times may not be as simple like 50%. They can be like 40%, 35%, and something like this. In such cases, in order to accurately draw exact segment, exact pie here in a circle, would need specific angle, right? Like to draw specifically how much, like we need exact this angle we need in order to draw the exact pie for that percentage. So we can convert these percentages into angles. Okay, and based on those angles we can draw exact pie sizes or exact these segments of a circle in a pie chart. And to find out angles, what do we need to do? We know that a circle is a complete circle is nothing but 360 degrees. Okay, a complete circle, 360 degree. Okay, and 50% of this 360 degree is half of this 360 degree. Okay. And why do we say half of this 360 degree? Why do we say 50% is half? We say 50% is half because this 50 is 50 from 100. Okay, we got 50 from 100 means we got 50%. Okay, and 50 from 100 or 50 divided by 100 is nothing but 1 by 2. Okay, so 1 by 2 of this 360 complete 360 degree circle is 360 divided by 2 is 180 degrees. Okay, so this angle is 180 degrees. I mean, this angle is 180 degrees. Okay, this line and 180 degree is representing, this 180 degrees representing 50% of the circle. Okay, similarly 25 is how much? 25 of 100 is 1 by 4. So 360 degrees by 4 is 90 degrees. Okay, so this angle is 90 degree. Okay, this vanilla flavor is 25% of the whole circle. That means it is 25% of 360 degrees, and 25% is 1/4 of 360 degree, which is 90 degrees. Okay, similarly, for example, if it is 40, then 40% of something, then 40 is nothing but 40 divided by 100. Okay, so that means it is 2/5 of 360 degrees. Okay, so 360 into 2 divided by 5, 2/5 of 360 degrees. Okay, 72 into 2 is 140 plus 4, 144 degrees. So to represent 40%, we need to draw 144 degrees. Okay, so we'll have to take a protractor and draw 144 degrees, something like this. Okay, to draw an exact, if we draw an exact angle of 144 degree, we'll make it 40% of this circle. Okay, section 5.5, chance and probability. Okay, and in this chance and probability, we will discuss what a random experiment is as well. Okay, so what a chance and probability, are they different? No, they are related. They are related terms but having different meanings. Okay, but they are related. Now what is chance? For example, you roll a dice. Okay, so a dice is having how many possible outcomes? 6 possible outcomes. If you roll a dice, 1 can come, 2 can come, 3 can come, 4 can come, 5 can come, and 6 can come. Side with 1 dot can come, side with 2 dots can come, side with 3 dots can come, side with 4 dots can come, side with 5 dots can come, side with 6 dots can come, right? So these are in the normal dice. These are the side. There are 6 sides in a dice, and which is having different number of dots from 1 to 6, and any of those can come. So what is the chance that one comes? That chance is, if for any one dot, number of dot, any one side to come in a dice is 1 in 6, because there are total 6 sides, right? So any of the sides can come. So the chance is 1 in 6. That's how we tell chance is. Like, chance is 1 in 6. When we roll a dice, chance of getting one side, any one side, is 1 in 6. Okay, we toss a coin, so the coin is having 2 sides only, right? Head and tail. Okay, so there are only 2 sides. So chance of either side to come is 1 in 2. 1 in 2. Okay, so there are two possible outcomes. So the chance of one side to come is 1 in 2. Okay, in case of a dice, chance is 1 in 6. Like, okay, and now what is probability? Probability is it's kind of likelihood of an event. Okay, so and probability is 0 or 1 or in between. Okay, 0 or 1 or in between. 0 means it's impossible. Okay, it can't happen. It's zero probability. Okay, so we say this thing is having zero probability, means it's impossible, it's not going to happen. Okay, it will not happen. 1 means it's having 100% probability. Okay, it is going to happen, definitely going to happen. So it's 100%. So, and in all in between. Okay, so 0.1 is in between, 0.2 is in between, 0.12 is in between, so on, and 0.123 is in between, everything in between. Okay, so there can be infinite decimal numbers in between 0 and 1. So all those are also valid probabilities of different experiments. So what is random experiment? Random experiment, this is a random. Rolling of a dice is a random experiment, because when we roll a dice, we don't know what side is going to come. When we toss a coin, we don't know which side is going to fall the coin on. Okay, so these are random experiment. And what is not a random experiment? For example, like there is a box, and this box is having all 1 rupee coin in it. Okay, all 1 rupee coin in it. Okay, so we have an experiment, like we want to pull out a coin from here, and now we are checking like whether the coin, what value the coin will have. Okay, whether it's going to be a 1 rupee coin or 2 rupee coin or 3 rupee coin, so on and so forth. But we know for sure that all the coins in this box are 1 rupee. Okay, so then it's not a random experiment. We know all coins are 1 rupee, so definitely when we pull out a coin from this box is going to be a 1 rupee coin. So there is no chance going on. Okay, there is no randomness in this event. So where is the randomness? When we toss a coin, when we roll a dice, these kind of events are, whether it's going to rain today or not, that's a chance. Okay, there is a forecast, but it's still, forecast can, it's not definite. Sometimes the forecast is there, but still, that's not deterministically. We cannot say that there is definitely going to have a rainfall. Okay. So these all events, these all experiments are when we experiment on things for which the results are not deterministic. So those experiments are random experiments. And chance is like they are related terms, as you have said that for the same thing, rolling of a dice, for a side to come, chance is 1 in 6. And if you say that like represent this thing in terms of probability, then the probability is 1 divided by 6. Okay, so which is close to 0.166666 probably, so which is kind of 0.17. Okay, so this is the probability. This number is always going to be in between 0 or 1, including 0 or 1. Okay, so this number, the probability is going to be in between 0 or 1. 0 is impossible, 1 in 100%. Probability, definitely it's going to happen, and everything in between. Okay, so all these possible values or probabilities are in between 0 and 1. Okay, including 0 and 1. Okay, now let us talk about 5.5.1, getting a result. Now we do any random experiment, okay, and we get a result. So for example, we are starting a scooter, okay, and sometimes it can turn on, sometimes it may not. So we apply a kick. Okay, let's say it's a kick, or like there is a button which we need to press in order to turn on the scooter, or we need to move a key and we need to turn on the scooter, and either it is going to turn on or it is not going to turn on. So for starting a scooter, there are two possibilities. One, there are two outcomes. Either it will turn on or it will not turn on. Okay, not turn on. Like it's not a possibility that it will turn off. When you are starting a scooter, assuming that it's in the turned off state already, right? So it will either turn on or it will not turn on. Okay, it will not turn on. Okay, so two possibilities. When we roll a die, so we know that the die is having 6 sides, and so when we roll a die, either of the side can come up. Okay, either of the side can come up. It's having 6 sides, which is having 6 different dots there. So 1, 2, 3, 4, 5 and 6, from 1 to 6. So there are possible outcomes are 6 possible. Either 1 can come, 2 can come, 3 can come, 4 can come, 5 can come, or 6 can come. So when we so the result can be any of these. So there are 6 possible results when 6 possible outcomes when we throw a die. When you spin a wheel with 3 options in it, okay, so there is a wheel and it's having 3 options in it, right? There is a needle. Here you win some, let's say here you win a car, here you win a motorcycle, here you win a simple bicycle. Okay, so there are 3 possible outcomes. Okay, how many? 3. This when you roll a wheel, this needle is going to roll, and it can be on any of these 3 options. Okay, and when it can be on any of these 3 options, there are 3 possible outcomes to this experiment of spinning a wheel which has 3 options in it. Okay, so possible number of outcomes are 3. List of outcomes from a bag of 5 identical balls of different colors. Okay, so in that case, like so you have 5 balls of 5 different colors, and you're pulling out a ball. So from this box which is having, from this bag which is having 5 identical balls, right? So any color can come out. Say for example, it's having red, it's having green, it's having blue, it's having purple, it's having white. So these are 5 colors. So you pull out a ball without looking at it, right? You're just pulling it out, and so any color can come out, right? You're not purposely looking into the color and pulling it. You're simply putting your hand into the bag and pulling out a ball without looking at it, right? So then any color can come out because all these are identical. There is no special feeling to a ball, kind of, right? So any color of the ball, any ball can come out, and that can be, so possible number of outcomes are 5. Next subsection is 5.5.2, equally likely outcomes. So what is equally likely outcomes? So in a random experiment, like we have seen an example of tossing a coin or rolling a dice, so the outcomes in rolling a coin was, for example, either head is going to come or tail is going to come, right? So if this coin is not tempered with, right, it's not designed a certain way where the likeliness, like head is going to come more likely than, like it's not tempered, it's a fair coin. So there is a term called fair coin, fair dice, like in probability we call it a fair coin. Fair coin means like it's a fair coin, there is no bias in the coin. Okay, so when there is no bias in the coin, it's a fair coin, then the likelihood of either head or tail is equal. Okay, head can come and there is an equal likelihood that a tail can come. Okay, we do not know which one is going to come, and there is a equal likelihood of any one of these sides can come up. Similarly, in case of fair dice, there are 6 sides to a die. On a die, there are 6 sides. Okay, so when we roll the dice, any side can come up. So if it's a fair dice, there are equal chances of 1 can come, or 2 can come, or 3 can come, we don't know, or 4 can come, or 5 can come, or 6, all 6 can come. Okay, so there are equally likely outcomes. Okay, so there is no bias in that. So it's a fair dice, it's not having any bias, it's not tampered with. Okay, chances of any of these sides coming are equal. Okay, so for example, in case of a coin, chances are 1/2 for head and 1/2 for tail. Okay, probability of coming 1 in 2 for head chance, and 1 in 2 for tail. Okay, probability is 1/2 for head and 1/2 for tail. Okay, so 50% for head, 50% for tail. Similarly, in case of a fair dice, probability of coming 1 is 1/6. Okay, probability of having 2 is 1/6. Okay, probability of 3 coming up is also 1/6. The probability for all these sides are equally likely. Okay, and all are 1/6. Okay, 1/6 for each of these 6 sides. So they're equal. These are called equally likely outcomes. So with this explanation, we have essentially covered subsection 5.5.3 as well, which is linking chances to probability. Okay, so what we have done, like head and tail, like a coin can have either of these 2 sides. So the chances of either side coming up is, when we toss a fair coin, is 1 in 2. Okay, and the probability is 1/2. Okay, for head, and 1/2 for tail. Okay, and chance for coming tail is also 1 in 2. Okay, so this is how their chances and probabilities are getting linked. We have already seen it in the previous subsection. Now in this subsection 5.5.4, let us try to distinguish between outcomes and events. Okay, so what are outcomes? Outcomes are possible outcomes of a random experiment. For example, rolling a dice, possible outcomes are 1 can come, a side with 1 dot can come, a side with 2 dots can come, side with 3 dots can come, a side with 4 dots can come, a side with 5 dots can come, or a side with 6 dots can come. Okay, so number of possible outcomes from a dice roll is 6. Okay, there are 6 possible outcomes from rolling of a dice. Now what's an event? Like, so events are essentially group of outcomes. Okay, so group of outcomes having a common property. Okay, so for example, an event is coming up an even number of dots when rolling a dice. Okay, so possible outcomes are 1, 2, 3, 4, 5, 6. 1 can come, 2, 3, 4, 5. Any of these number of dots can come. These are possible outcomes. But possibilities of 2, 4, and 6 even numbers to come. So basically group of outcomes. We are grouping these outcomes together, 2, 4, 6. And what is common between 2, 4, 6? These are even. They are, what is the commonality between among 2, 4, and 6? That these are even numbers. So that's an event. So outcomes were 1 to 6 possible outcomes, and event is getting an even number. So these outcomes, these three numbers in this case, have been grouped, and getting an even number is an event. Similarly, getting an odd number is an event. In that case, these three numbers would get grouped together, 1, 3 and 5. Okay, so that's an event. Getting an odd number is an event. Getting an even number is an event. Any sort of group we can form which is having multiple outcomes with a common property. Let us take an example which highlights these differences, difference between outcomes and event. So for example, we are having a bag, okay, and this bag is having 4 red color balls, okay, 1 2 3 4, okay, and it's having 2 yellow balls as well, 1 2. Okay, so 4 red balls in it and 2 yellow balls in it, and probability of getting a red ball when we are not looking into the bag, when we are not looking into the balls and then just pulling out one ball, so probability of getting a red ball. Okay, so there are 4 red balls, so possible outcomes are, so how many balls are there? 6 balls are there, so there are 6 possible outcomes, right? So because there are 6 balls and any of those balls can come out, right? So there are 6, how many? 6 balls are there, so 6 outcomes. Now we are looking at the probability of pulling out a red ball. Okay, so how many red balls are there? 4 red balls are there, right? So this is a group, right? So that's an event here, right? Getting a red ball is an event here because there are 4 red balls and they are in a group. Okay, so how many red balls are there? 4 red balls are there. And how many total outcomes are possible? 6 are possible. Okay, so probability of getting a red ball would be 4 divided by 6. Okay, so 4 red balls and total outcomes are 6. There are total 6 balls in it. So probability of getting a red ball is 4 divided by 6. Like in case of a head and tail, in case of a coin, 2 possible outcomes. Probability of getting a head is 1 divided by 2. Okay, similarly here in this red ball, how many red balls are here? How many head was there? 1 head was there. How many tail was there? 1 tail was there. So 1 head divided by total head and tail, 1 by 2 was the probability of getting a head in case of a tossing of a coin. In case of this, how many red balls are there? 4 red balls are there. How many total outcomes are total number of balls? 6. So this is why probability of getting a red ball is 4 divided by 6, which is nothing but 2 divided by 3. Probability of getting a yellow ball event, for example, is getting a yellow ball is an event. How many balls are there? 2 balls are there. 2 yellow balls are there. And how many total outcomes are there? 6. So probability of getting a yellow ball from this bag of 6 balls is 2 divided by 6, which is 1 by 3. Who is having more probability? 2 by 3 is greater than 1 by 3, right? Because denominator is same, numerator is bigger here, so 2 by 3 is bigger than 1 by 3. 2 by 3 is close to 0.666 and 1 by 3 is close to. So basically we can put this to a formula that this 4 is number of outcomes that make an event. So how many? There are 4 red balls, so number of outcomes are there are 4 outcomes which make this event of coming a red ball out. Okay, so formula can be probability of an event, and what's an event? Coming out a red ball. Okay, so probability of an event is number of outcomes that make an event. Okay, so this 4, number of red balls, so number of outcomes, total outcomes were 6 because there were 6 balls in it in the bag. Number of outcomes that make an event, And event, we have already seen, event is basically a group of outcomes which have common property, and in this case these are all red balls, so that's having a common property. So such outcomes are 4 which have common property of being red color. Okay, and total number of divided by total number of outcomes, total number of outcomes. Okay, so that's a formula. Okay, chances and probability related to real life. Okay, maybe pulling out a red color ball from a bag and pulling out a yellow color ball from a bag may not be real life cases, but there are many real life cases in which probability mathematics can be used. For example, evaluating the chances of any weather event, whether it's going to rain or it's not going to rain, what are the chances it's going to rain, like we can use probability, and many other things such as whether the share market is going to go up or share market is going to go down, whether a particular election result is going to go in favor of this party or that party, or to in favor of this candidate or that candidate, or to all these real life situations can be put to test with probability mathematics. So before ending this data handling chapter, let's discuss one more small thing, like